just moved, I gather, from Cornell to Rutgers, and he's going to speak about statistics for big data, compressed sensing, search, and learning.
Thank you. I try to tell people several interesting stories. Many of the stories actually never really published, but they're so interesting, so I must tell people. So the first story was about something interesting about compressed sensing. So let's start with a simple example. So suppose we have a signal with only two non-zeros. But we do not know. But we want to recover the signal, but we do not know the signal. And we do not know the location or the magnitude of the non-zero coordinates. In fact, the entries can be time varying, like data streams. And so, as in compressed sensing, usually what people do is that we want to do a linear non-adaptive measurements by doing this xi times s. So this is S is called design matrix, so which is a manually generated or hardware implemented, like for example in the camera. So for this particular example, so this is what we know because that's how we do it. But for this particular signal, this measurement is actually only these two guys. So I choose this example just for simplicity. So there's something very funny about this example, is that suppose now we have this, we have the measurements, and we generate this S. It's design matrix. It's called design matrix means we can design it. So we know Y, we know S, but we want to recover X. So what we do is, suppose you take the ratios, because we can always do it, right? For every coordinate, because we know Y, we know S, so we can always do it. And look like it's interesting thing is that the 1 is the truth. So the measurement in terms of ratio statistic is actually the truth contaminated by this guy. So the interesting observation is that if we make this S1, S2, the ratio to be either 0 or infinity. So what's going to happen is if it's 0, then that's the truth. If it's infinity, then it doesn't work. But if one is infinity, the other one is 0. So the other one is going to work. So that's very interesting. So now let's see what's our algorithm. So our algorithm works like this. Now suppose in the first measurement, S2 of S1 is 0. Then the first coordinate is to recover the truth, but the second coordinate is useless. I mean, in terms of the ratio statistics. So now in the second measurement, suppose the ratio is infinity, then the first coordinate is useless, but the second one you see is the truth. Now on the third time, one of them has to be good, right? Now let's say the first one is good. So now what's interesting here is that now you see something reasonable twice. If you, of course, we have the theory to prove that, to prove this, but in the intuition that if you see something reasonable twice, it got to be the truth. So this is basically, for example, if you got paper rejected twice, maybe you have to really revise it substantially. So, okay, so now let's estimate x1 equal to 1, because we see 1 twice, right? So once you estimate x1 equal to 1, then we do the same thing. So the next iteration, we just need to use a residual. Then use a residual to do the ratio statistics. Now everything is 1. So you see the reasonable thing 3 times. So it has to be 1. So the second coordinate has to be 1. So now we get the second coordinate right. Now the third time, the residual becomes 0. Then all the 0 coordinates is recovered. So the importance and perhaps surprising consequence is that you only need 3 measurements for k equal to 2 non-zeros, regardless of the length of the signal. Yeah, so this is the work is still ongoing, but I think there's something extremely interesting, perhaps very exciting here. So now, how do you realize the ideal design? So the ideal design can be realized by sampling S from alpha stable distribution with alpha go to 0. The standard procedure for generating alpha stable is a general uniform, a general exponential, a general uniform. Then you go through this complicated formula, which can be replaced by central limit theorem. You can actually, this guy's good enough in practice. But if you like complicated formula, this is a formula for generating alpha stable. So stable means the weighted sum of two stable is also stable. Now the scale is exactly the L alpha norm. Yeah. So now we look at the ratio, right? So we're interested in the ratio. So if S2 over S1, so the absolute value when alpha is small, in this case is 40% 0, 40% infinity. There's something in between. But when alpha is, for example, extremely small, and 50% 0 and 50% infinity. So, of course, in practice, we cannot really use alpha equal to 0. We have to use small alpha. So in my MATLAB simulations, I did the experiments for a year, and I realized alpha equal to 0.03 give a very good answer. But I have to continue doing the experiments. But it looks like at least for the things I tried, 0.03 works very well. And we have a theory to show the performance for any given alpha. So alpha has to be small for that particular algorithm, but it's very promising. So now, once we're convinced that the ratio is either infinity or 0, now it makes sense. Because, so indeed, it's in 0, infinity, now we can recover this guy, and in second iteration, we can recover the second coordinates. So that's the story. So it's an interesting thing that the two coordinates are competing, right? So the second coordinate is bad, not because it's bad, just because by chance the first one is good. So this is basically like when you're taking a class and someone get A and you get B, not because you're bad, because by chance someone else get A. So but in order for you to get A, one suggestion is you have to remove that guy, then you get A, right? So that's basically the algorithm, how it works. Okay, so there's a series of work, and we're still writing. So we're accumulating lots of results, and we have to be selective how to present because this kind of is an strange idea. So the whole bunch of questions can be asked. The problem if you answer all the questions, then basically nothing left, and it's also very hard because there's so many things that can be done. So basically, I'll propose using alpha small for alpha is 0 to 1. For example, in compressed sensing, we usually make the assumption that the signal is within the L alpha ball, right? So I think there's a very strong connections there. And especially for small alpha, the performance is especially good. It's computationally very efficient because only one linear scan, and extremely robust to measurement noise. And robust to measurement noise because we're using ratios. And this is very stable. It's a very heavy tail. If you're adding some noise on the top, it doesn't matter. And using fewer or almost the same measurement compared to linear programming, and the design matrix can be made very sparse. So the design matrix can be made sparse, so this step can be done essentially trivially. And since I've been working on these things for quite a while. So that's the paper we like to promote is called compressed sensing meets compressed sensing. Compressed counting meets compressed sensing. So you will know what I mean by compressed counting. So what I mean by compressed counting? So basically, most of the natural signals, like images, are non-negative. Instead of using symmetric stable projections, you can use skewed projections, and which has significant advantages. And we have several papers on how to use skewed projection, which I call compressed counting. I'm going to give you more applications about compressed counting later. And for this paper, we have a results shows that you can get a very good recovery if your alpha is between 0 and 0.5. So this is theorem. So basically, suppose the signal is non-negative, and we're using alpha stable, maximum skew stable projections. It suffices to use this many samples. So there's a constancy alpha. So the error is actually epsilon alpha. So usually we see the error as 1 over epsilon squared, right? So this is 1 over epsilon alpha. So that's actually the significant difference. And if we use one scan algorithms, so what is the C alpha? The constant you can actually exactly calculate. So for the constant is 0, between 0 and pi over 2. You can actually plot everything. So when alpha is 0, the constant is 1. When alpha is 0.5, is pi over 2. The calculation for alpha larger than 0.5 is too complicated, and still working on it. But I think the most exciting part is alpha not too large. Yeah. So the numerous extensions and improvements. So basically, so this is a compressed counting one scan results. However, if the signal can be negative, just using symmetrical projections, that's not a problem. When alpha, particularly interesting case, when alpha goes to 0, this epsilon alpha is actually 1. This means you can actually accomplish exact sparse recovery. And of course, there's some precision. You have to work out the precision of the signal, etc. But conceptually, this leads to a very efficient exact sparse recovery algorithms. And also, you can use a slightly more sophisticated, instead of just one scan, we can do multiple scans. I mean, multiple iterations. You only scan the long sequence in one time, then you work on the iteration on the small number of undecided points. So it's, the cost is still roughly one scan, but you can substantially improve because of this nature that the error go to 1. The error alpha power go to 1. Just like the example we show you, the k equal to 2 case. And of course, the design matrix can be made very, very, very sparse, and almost little impact on the recovery results. So let's look at some simulation results. So basically, this is zeta means I'm using k log n. So m0 is k log n. Then in zeta means I'm using the measurements at m0 divided by zeta. So using smaller number measurement, then you see which method fail at which point. So linear programming and OMP, they fail roughly here. And our methods are still doing pretty well with one scan. With multiple scans, it's still doing better. Yeah. So ultimately, our method also fail. But it's doing a lot better. And also, when it does fail, it still provides partial recovery. So this is of course, it's much faster as well. So this is an example of what I mean. People talk about single pixel camera. So basically, suppose you have a sparse images. Usually, the image is not sparse, but the difference could be sparse. So basically, suppose you have a surveillance camera pointing at one angle, and you want to find anomalies, right? So you look at the differences. So usually, there's nothing, especially when the time is very close. You see nothing in the difference. But if an anomaly happens, you see some difference, which is sparse. Anomaly and sparsity is usually it's an acronym in some sense. So now, how do we recover this? So basically, we're using k log n divided by zeta, so reduce. So k log n is what we believe a standard comprehension algorithm will produce, will require. But if you reduce the number of measurements, so this is using standard number of measurements, we get this result very good. Divided by 3 is very good. If you only using 1/15 of the required number of measurements, you still get good results. So this is interesting because the recovering algorithm does not take advantage of the structure at all. But so there's even more possibility of further improvements. So human can still detect this 5 and 4. So summary of the contributions on compressed sensing is that sparse recovery is a very active area in research in many disciplines, in math, CS, and EE, and perhaps also in statistics. So in classical settings, design matrix for sparse recovery is a sample from Gaussian design, where alpha, which is alpha equal to 2 stable. So if you're using alpha stable with alpha very small, you need to simple, fast, and robust and accurate exact recovery. The cost is one linear scan, and there's no catastrophic failure. It means you can still see useful information from here. So the design matrix can be very sparse without hurting the performance. This connects to the inferential work with sparse matrices for sparse recovery. This is just very preliminary work, and there are numerous research problems and applications which we'll study in the next few years. And perhaps I will ask someone in the audience to work together, since some of the problems are so interesting, and it's actually outside our capability to solve, for example, some of the optimization problems. I find it will be very exciting. So that's a story about compressed sensing. Which we use alpha stable with small alpha. So what about other applications of stable random projections? So stable random projections, basically you have the signal, you multiply a dot product with the design matrix, or this S is what you generate manually, then you get your measurements here. So what other applications this thing can do? So basically, we can use this to estimate the L alpha norm or L alpha distance. For example, in machine learning, this is special advantages when the data is streaming. And we can also use if beta equal to 0, this is symmetric. If beta is 1, it's skewed. If you're using skewed projections, which we call complex counting, makes the entropy estimation problem as a trivial problem. Now you only need 10 samples. So another interesting thing is that if you're using skewed symmetric projections, which also makes the entropy estimation problem trivial in general data streams, like 100 samples are needed. So those are very interesting, and we always, so all of this basically we have the theory and we have the experiments. So it's my belief that good theory always leads to good practice. So what are other things? For example, if you're only using so now there's coding issues. So if you're only using, if you use a real value, you get some results, but if you only use the sign, you actually get a very interesting results, because the sign is also very useful, not only for learning, you get a very efficient learning algorithm, you also get a very efficient sublinear time near neighbor search algorithm, because the sign is a 0, 1, provide the indexing. So one problem I've been thinking for a long time, maybe since graduate school time, is that if you're using S not normal, if you're using Cauchy, so what's the probability that the signs are equal? So I've been thinking about that for many years, but until recently we had a guess, and the guess turns out to be very good. Is that the collision probability is close to chi-square. I mean, the chi-square probability and chi-square similarity, which is very popular in computer vision. And so we just had a paper recently. So this is with my Cornell colleague. So Gennady is a probabilist, and John is a theoretical computer scientist. So not only just use a sign, you can actually do better than just a sign. So that has to do with coding. How can you code a 64-bit number using a few bits? So we have another report. This is how can you code random projections. So basically, is that if you use 2 bits, usually you get a very good trade-off. So 1 bit is 2 ways, and 2 bits is pretty good. Yeah. So that's lots of interesting results here. So we mentioned about the applications of data streaming and the entropy estimation. So let's give a quick review. So what mean by data stream? So massive data generated on the streaming fashion. So basically, what about streaming fashion? So basically, suppose so A is a vector, but the entrance of A changes over time. So every time, one of the coordinates gets updated by this amount. So this is called Turnstein streaming model. And so one popular thing to measure is what's the frequency moment and what's the entropy. So this is an example. So this is the DARPA conference in 2003. I reproduced the figure because the original figure is not visible. It's not very nice. So I reproduced the figure. So basically, you can view this horizontal axis as time, and the measure the entropy. So during the time when the attack occurs, they'll observe the entropy change, the sudden change. So if you're able to capture the entropy change using a smaller number measurement very fast, then there's a chance that you can find the denial of service attack. So that's an interesting problem. And in practice, what people do is, because the entropy is basically the first derivative or the first moment. So what people do is just using the finite difference. So this is another way to write a finite difference. So if you estimate the alpha moments and the first moments, then you go through this formula, you will converge to the entropy. The immediate problem, as we know that in statistics, is that if you have if you estimate this guys, and the variance is proportional to the constant square. So the variance is proportional to 1 over alpha minus 1 square. So that's a huge constant. If you view that as a constant, it's a huge constant. Because we want alpha go to 1. But this guy, the variance is proportional to this to the square of it, 1 over the square of the difference. So practically, people really need like millions or billions of samples. It turns out you only need 10 samples, or maybe 100 samples, by doing good statistics. So that's the trick. So the trick is suppose the data non-negative. So here we need to estimate both, right? So what people do is they estimate them separately, then they compute this guy, which leads to a huge variance or a huge constant. So basically, when the data are non-negative, if data are non-negative, the first moment is actually the sum, which is just can be computed error-free. So you only need to estimate one thing instead of two. However, if you estimate the other guy using maximum skew projections, the variance turns out to be proportional to alpha minus 1 square, and which is exactly what we need here. So you actually cancel it, because so the intuition is this: if the first moment is error-free, 0 variance, the alpha moments near alpha equal to 1 has to be very easy, because we live in a continuous world. So it's really a matter how fast it converges to 0. It turns out the algorithms, the speed is actually alpha minus 1 square. So everything just works out nicely. So the estimate look like this. So you do the projections. You do alpha stable with beta equal to 1, maximum skew projections. You go through this formula. And I admit that initially I guessed the formula. After staring at that for a couple of years, I guessed it. But then it turns out a very good guess. And it turns out the variance is very small. So now, with the 10 samples, the mean square error here is extremely small. So 10 samples provide very good estimate. So you don't need a billion sample. You don't need a million sample. You don't need a billion sample. You only need 10 samples. Because we take advantage of the fact that the first moment is error-free, and the second moment, the alpha moment can be computed very fast, very accurately. So the problem seems to be solved. However, then my friend at Georgia Tech, they told me that they often care about the difference of two streams, which means if you care about the different two streams, then it's problematic. Then, because then the absolute value is no longer the sum. So we still have to use the symmetric projections if you care about difference of two streams. So the Georgia Tech guy, they're network guys, so they know better about the practice than I do. So what they do is so they basically have to use the symmetrical projections. So then I look at these problems. So if you, what my friend at Georgia Tech did is that they basically said, well, let's make them separately estimate them, and then you get this guy. From a statistical perspective, if you make these two highly correlated, actually I shouldn't use correlate because correlation is not defined. It's highly dependent. I had this guess and write my proposal in 2008, but I didn't fully solve it until 5 years later, because the idea works, but the analysis is very hard. So basically, if we make the two almost the same, then the variance, for example, if the two are the same, right, then the variance is 0, but of course they're not good. But if they make two almost the same, then the variance is also small. So how do we make the two estimates almost the same? So that has to do with how we generate the stable distribution. Again, we generate stable distribution with uniform and exponential variable and go through this formula, which is a function of alpha. And so we can change alpha. We can use the same U and W with different alpha. Because alpha is close to 1, then we expect they're highly dependent. But dependency is very complicated. It turns out, so we make this two highly dependent. It turns out the two estimate has to be very bad. If we use good estimate individually, very good estimate, you need to improve results, but not good enough. The two estimate have to be very bad. They're so bad that they don't have any variance. Then the ratio is good. So that's another things amazed me for a while, but that's, of course, our analysis showed that it's indeed the case. My guess is that because these things, if the both are very bad, then a little bit of fluctuation doesn't matter as much because they're very, very bad. So bad over bad is actually good, is good. So, which happens in practice sometimes, yeah. Yeah, okay. So basically we generate, so we do the correlated or dependent stable random projection. One uses alpha equal to 1, one uses alpha equal to alpha with alpha small, close to 1. Then use this stranger estimator. They're both bad estimators, but the results are very good. And, and we can analyze that the variance of this guy is actually constant and divided by sample size. Because, just because of, I'm using bad estimate for both, and they're highly dependent. So it turns out using like 100 samples give very good results. So again, for this more complicated case, we do not use a billion sample, we do not use a million sample, we use 100 samples. So that's the story about the, how many minutes I have? 10 minutes? Okay, that's enough. Good. Okay, so that's the story about the streaming data and estimations using correlations and using skew projections. So those are very exciting stories. What bothers me, has been bothering me for a while is that, because I hope that like, I develop something really works. So suppose someone going to take and use it. But the things that when I talk to industry people, they really care about those things. They say, well, for the network, I think people actually they try to approach me, and they say they're going to use it, but they're not going to tell me if they really use it, of course. But for a lot of those high-dimensional data work, so we hope to make a practical use of it. But it turns out in practice, what people really care often is the high-dimensional and the sparse and the binary data. So this make and it turns out stable random projection is not good anymore for binary, high-dimensional, sparse data. So that's a problem. And I illustrate this by our work on machine learning with big data. So basically, what people do in practice, they want to use a simple method like logistic regression, SVM, and they use lots of data. And so the data matrix is just very large in both directions. And here's the one simple task. Suppose you have your features, if, for example, in 2 to 64 dimensions, and you want to predict y is 0, or minus 1, or 1, and you fit this logistic regression or SVM. So C is regularization parameter. You want to learn the weights. So even for such a simple problem, could be challenging because the data cannot fit in memory, and data loading can take too long, and training, solving this problem can take a long time, and testing can take a long time. Why testing can take a long time? Because if the weights are known, you still have to take the inner product. So that can take a long time. Depends on your application. For example, if your application is in search or high-speed trading. So this motivates us to do dimensionality reduction and data reductions. But data reduction means reducing number of non-zeros. So with the modern algorithm, which is often linear algorithm cost for story and transmission computation often determined by number of non-zeros, not much about the dimensionalities. So let's look at an example. So basically, suppose you have the Webspam data. If you're using like 1 gram, means the frequency of each characters. 254 is very close to 255, which is the size of ASCII table. So there's one is not used. So they get a 93% to represent a text. So if they use 3 grams, so the dimensionality is increased to 254 over the 3rd power, which is about 16 million. So they get almost 100%. So and use linear algorithms. If you say, well, can I do better by using non-linear algorithm? So no, it doesn't help. It only takes you more time, doesn't help. So for high-dimensional data, linear algorithm really suffices in at least many practical scenarios. Another interesting about high-dimensional data is that only binary information matters. So basically, if you use low-dimensional representation using binary representation, it's not as good. But for high-dimensional representation, and if you binarize it, it's very, very good, still very good. You don't lose the information. So for high-dimensional But in a sparse case, really only the presence or absent information really matters. So that's an amazing thing, which is disappointing because that limits how much we can do. And so it's good to use high dimensional representation, but that generates a high dimensionality and high storage costs. So what I heard from the search engine, what they do is that they use high dimensional data and learning algorithm, then plus hashing. So in case some people in statistics do not know enough about hashing, so I'm using the example random projection as an example for hashing. So basically, if you want to build a statistical model for this data, they say, well, it's too high dimensional, I cannot handle it, so I can multiply by matrix R, then I get a small matrix B. And then I can build my model here. So how do you choose R? You can choose R from a very sparse matrix. So basically, we did this work in 2006. And basically, if you sample the matrix with 0 with extremely high probability, for example, 99% or 99.9%, and for high dimensional data, you can do 99.99%. It's still very good. So this is the data. So this is the same data. So 350,000 text examples, and with the task is predicting spam versus non-spam, and it's very high dimensional but very sparse because only 4,000 non-zero. But 4,000 is a small number, but it's actually a big number if you have a lot of them. And take up 24 gigabytes of that disk. So let's apply random projections and using the sparse projections and see what happens. So basically, the interesting thing is that you need to use lots of projections, like 4,000 or 10,000 projections. However, the projection matrix can be extremely sparse. For example, S equal to 1,000. What S equal to 1,000 mean? Means 99.9% entries are 0. So there's two interesting things. Very nice story. However, 4,000 projection or 10,000 projection is too big a number. So what we can do better in this case. So instead of doing projections, what we'll do is we can do permutations. Instead of projection, we'll do permutations. And instead of using 10,000 projections, we can use 200 permutations. And the work is inspired by something called Minwise hashing. So basically, what Minwise hashing is doing is, suppose you have binary data, and you permute the columns. This is all conceptually. In practice, you don't have to generate the matrix, of course. You permute the columns, and you store where the first location where it is non-zero. So for example, in this case, the hash value is 2, 1, 0, and 0. So then you repeat. Suppose you repeat 3 times. The hash values are the guy, this guy, and this guy. And one of them is equal. That means the similarity is 1/3. So basically, that's how it is done in practice. But then people complain that you need 64 bits to store each hash value. So store this number, take 64 bits. Why? Because it's very sparse. It means this guy can actually happen almost anywhere. So what people do is using 64 bits. So this generates a big problem. So what we did is instead of using 64 bits, let's using a few bits. And then we realized that if you're only using a few bits, before the dimensionality is 2 to 64, now you only go to 2 to the B. If B is like A, like 1 byte, the dimensionality is actually very reasonable. You can actually, from high dimension to small dimensions. So taking the bits not only reduce the data, but also reduce dimensionality. And then, when I talk to my friends in search engine, they say, well, they want to find a way to reduce the number of permutations. Then actually, we solve the problem for them. They say, well, instead of using K permutations, you can use 1 permutation with K bins. And all this accomplished by doing basic statistics and probability. Maybe 2 minutes, it should be done. Yeah. So basically, what is really doing here is like this. So we do Minwise hashing. We generate hash values, and we only take a few bits. But conceptually, so instead of this big number, it becomes a number between 0 and 3. But instead of, in order to get an inner product, you have to do the trick. I try not to explain the trick, but the trick is basically you have to represent the location, the value in terms of the location. I mean, in terms of the matrix, the vector we're going to use. for the classification. So basically, so end result is that you start with a high-dimensional binary feature vector, you get a low-dimensional feature vector, and still binary with a few non-zeros. Now let's see how it works. So basically, if you use 200 permutations, and 1 bit, you achieve pretty good, reasonable results, but 2 bits, better, 4 bits, even better, 8 bits, you get the same results as original. So originally, which take 24 gigabytes, but with 8 bits and the 200 permutations, you need about 70 megabytes. So it's very good results. And the training time is substantially reduced, and testing time is substantially reduced. Then people asking me is, how can you, so they say that's cheating because you don't consider the time to do the permutations. That's true, but we don't do the permutations. So basically, the permutation can be done either parallelized by GPUs or by statistical methods, only use 1 permutation. So basically, before what people did in practice, you only do 1 permutation, store the minimum, then discard the rest, which is very wasteful. So what we can do is instead do 1 permutation, do k-bins, and take a minimum each bin. So you can statistically show that there's actually even better result, better methods. And we can see that with the 1 permutation, k-bin is better than k-permutation methods. And so this is the best we can hope for. So we do better and a lot less work. So all of this, so some of the contribution of B-bit Minwise hashing is that we're only using B-bits as opposed to 64 bits in standard industry practice. And we discover linear kernel algorithms. And by this bit idea, we're only using 2 to the B dimensions instead of 2 to 64 dimensions, which leads to very practical, efficient algorithms. And we developed this 1 permutation hashing, which seems to solve the problem that the industry people really care because they have to do a lot of permutations. And we're go beyond. If you're still familiar with Google sets, we go beyond the pairwise. We now work on 3 ways or multi-ways. And so that's the contribution B-bit Minwise hashing. So now, so the final conclusion here is, so I think this is an exciting time for statistics and computer scientists because the researcher and practitioner often do not have enough knowledge of the fundamental data generation process, which is often, fortunately, compensated by the capability of quickly collecting lots of data. And for many statistical problems, often the approximate answer suffice. So that's a good thing. And hashing has become crucial in important applications, for example, search. And we developed a hashing for using with a stable random projection for compressed sensing. And these two are surprising algorithms for sparse recovery and a surprising algorithm for database learning and information retrieval. There are numerous research problems we still have to work on, but we have some good progress. In industry, the interesting thing is that for industry, they often expand the data extremely high dimensions. For those high dimensional data, often only binary data matters. So for binary data, we developed those B-bit Minwise hashing and the learning and search algorithms. So in a summary, I think a probabilistic hashing is really just a clever way of sampling. And I believe statisticians can make great contributions in those areas and practical contributions in these areas. We just have to treat them as statistical problems. We cannot say, oh, this is an engineering problem which statistical people don't work on. We only work on biology. But we hope that computer scientists and statisticians can work together, and so there are lots of exciting progress we can make. Yeah. Thank you. Okay.